start? Ah, sounds good. Okay, I'm going to take my phone out and close the door. Okay, so I just want to finish off some of the slides at the end of this presentation and then start talking about graphical models. Can everybody hear me okay?
Yes.
Raise your hand in the back if you can hear me. Okay, good. All right. Okay, so we finished off with Variational Bayesian EM as a way of doing approximate inference in a Bayesian model. It's very widely applicable to all sorts of models, like you see listed here. I showed you the example for mixture models. What I want to do is just talk a little bit about these further topics that I tacked on at the end. This includes some kind of interesting discussion material, and also I'm going to mention again this sort of relationship between parametric and non-parametric methods, which Peter Orbantz already talked about, and Dylan has already been talking about. Okay, so the first thing I want to talk about, this is like a random collection of interesting things that follows on from the general Bayesian framework. First thing I want to talk about is Bayesian discriminative learning. And the reason for that is that in machine learning, we have certain terminology, and that affects the way we think about different kinds of models. So one particular kind of terminology is this generative versus discriminative model distinction. So let's look at classification. When you have some inputs x and some class labels y, a generative model basically models what you could think of as the generative process for objects out there in the world. If you're trying to classify cats versus dogs, what you do is, let's say it's images of cats versus dogs, to be more precise. You have some prior proportions of, you know, how many cats versus dog images you expect to see. And then you have a class conditional density, which gives you, for each of your classes, a probability distribution over the observed features of that class. So this would be the probability distribution over image features, assuming you're a cat, versus another one, assuming you're a dog or a turkey or whatever. Okay. In discriminative modeling, what you do is you try to directly model the conditional distribution, which would be, say, the probability of the label given the class. Or you could be building a decision system that just simply outputs a hard decision about a label, given the input feature there. Okay? So it's often the case that a lot of machine learning is based around discriminative models, and the Bayesian bits of machine learning are often talking about generative models, probability distributions over the whole data. And so it's very natural that this sort of conception has emerged that the Bayesian Frequentist divide maps onto the generative discriminative divide. And that's not really accurate. It is perfectly possible to be Bayesian about a discriminative model, and similarly it's perfectly possible to build generative models in a frequentist way. For example, you could do something like kernel density estimation, or fit a mixture model using maximum likelihood or something like that. Okay? In particular, I think it's maybe useful to look at the example of linear classification. This is something we're all extremely familiar with. So imagine we have a few data points. Let's say these two blue data points and this one red data point. And we want to build a linear classifier. Okay? And clearly, all of these gray lines are consistent with this data set of 3 data points, right? All of these gray lines perfectly separate the blue class from the red class, okay? So how do we choose one of these to make our predictions? Well, if you look at the, let's call it the maximum margin principle for choosing these, it would say choose this blue line here, this blue dashed line. That's what the support vector machine will give you. It is the line that maximizes the margin, the distance to points in either one of these 2 classes in this noise-free classification problem. Okay? Now let's just contrast that with what some people have called the Bayes point machine. Sort of, it used to be, instead of restaurants and things like that, it was all about machines a while ago. So, the support vector machine kicked off a revolution in naming of machine learning methods to different kinds of machines. So the Bayes point machine corresponds to this very, very simple idea, which is take a distribution over linear classifiers. For example, in this case, a uniform distribution as your prior, okay? So uniform over all possible orientations. And then conditioned on your noise-free data here, your distribution over classifiers looks like this gray thing. I've sampled a few hundred points from that distribution. And the Bayes point machine just says, find the mean in parameter space of the posterior distribution over your classifiers. Okay, and that's what this red curve gives you. So what does that do for us? It says, well, first of all, the answer is different from the maximum margin classifier, and the difference comes from the fact that we have this data point here, which essentially eliminates, it makes the problem asymmetric. It eliminates a bunch of classifiers on this side, so it tilts the Bayes point classifier in the rightward direction. If we add one other data point here, I've of course chosen pathological examples to show you the differences, to exaggerate the differences, but if I add one extra data point here and one extra data point here, that maximum margin doesn't change at all, but the Bayes point shifts further in this direction, which is what you would get from just averaging over these guys here. And similarly, if I add a cluster of points here and a cluster of points here, none of which are actually support vectors, right? They're all further away from this blue line than these 2 points, but they act in the opposite direction, repelling the classifier in the leftward direction. So any questions about that? Bernard?
So you were mentioning the term noise before, and maybe it's a bit misleading because this one is not about noise, right? The difference between the Bayes point machine and support vector machine is
right.
Averaging, right?
Right. So this is not about hard versus soft classification. It's not about noise models or what I would call likelihood functions. It's about averaging. But Bayesian methods are all about averaging. Okay? That is the core idea. The core idea is, given this small data set, I have uncertainty about the classifier, and I need to average the predictions of these classifiers. This is not an exact Bayesian solution. What we do here is slightly incorrect, which is we're averaging in parameter space to pick a classifier. What we should really do is average the predictions of all of these different classifiers. That's what the sum and product will give you. But averaging even in parameter space for this very well-behaved problem gives us different solutions to what we get from maximum margin. And really, you can visualize this all very geometrically. You have data, and then that data constrains in parameter space the feasible set of solutions. The maximum margin gives you a particular point in that feasible set, which has the largest enclosing ball, and the Bayes point would try to average over that feasible set in a different way. Okay. It's just useful to illustrate this. Also, I do want to make the point that a lot of us, and you'll hear a lot more about it, work on Bayesian discriminative models, things like Gaussian process classifiers and things like that. Okay. Again, just to reinforce this kind of difference between parametric and non-parametric models. And I think I'll make an editorial comment at the end of this slide. Okay, so parametric models assume a finite set of parameters. In other words, if you want to make predictions given those parameters, the rest of your training data is irrelevant. That's what this is a conditional independence statement saying, given the parameters, the training data can be dropped in terms of making predictions about X. Therefore, your parameters capture everything there is to know about the data. In a sense, your parameters are, in a very strict and formal sense, your parameters are an information channel from your past data to your future predictions. Okay? And all of the power of your past data goes through that channel of information. And the complexity of that channel is bounded by the number of parameters that you have. And this makes them not very flexible. Even if you have infinitely much data, you can only learn a finite amount of information from that data. Non-parametric models assume the data distribution cannot be defined in terms of such a finite set of parameters, but generally it means that it can be defined in terms of some infinite dimensional parameter space. And we can think of that theta as a function or an unknown distribution or something like that. And the nice thing about that is that the amount of information about past data that can be used for future prediction grows with the amount of past data that we have. And that makes them more flexible. And another way to think about it is parametric models are really model-based. They're really like, you write down a particular model, you learn the parameters of that model. Non-parametric methods tend to be memory-based, because to make predictions, you need to actually store past data in some form, or store a growing amount of statistics of past data in some form in order to make predictions. So that's sort of the model-based, memory-based distinction. And I think maybe more important, I talk about the Bayesian versus more classical approaches, but I think more important than that distinction is this distinction between parametric and non-parametric models. A lot of the most successful things that have happened in machine learning, sort of the whole kernel revolution with support vector machines and all the other kinds of kernel methods, has really been based on the success of non-parametric approaches. Okay, it's the power and flexibility of non-parametric approaches that has made us able to do a lot better than what we used to be able to do with our small models. Even things like neural networks, these large neural networks or something like a deep belief network, these models have hundreds of thousands of parameters. Effectively, they're basically non-parametric models. They're so flexible that they can actually learn whatever's in the data. They let the data, quote, speak for itself. And that's sort of an idea that I think is quite powerful. Okay, any questions about that? Okay. Just as a preview, I think John Cunningham is going to be talking about nonlinear regression and Gaussian processes. I could actually skip over this so that I can get to, there's something making a very loud noise. The projector is overheating or something. Okay. All right, interesting. Do we have a spare projector bulb, or we're going to find out? Okay, that's good. Okay, so I'm going to skip over Gaussian processes just to say Gaussian processes define distributions over functions. Forget my polynomials example as a practical thing. You never really want to be fitting polynomials to data because you don't really believe anything in the real world comes from a polynomial. You want more flexible function approximators, and Gaussian processes are a way of defining flexible functions from data. You heard about Dirichlet process mixtures just now. maybe I'll just skip over this because you've already heard about it. A point I want to make is the importance of distinguishing in this framework between a model and an algorithm, okay? So Dirichlet process mixture is a model of data. And now once you define the model, you can think of many different inference algorithms for, you know, computing predictive probabilities from your model or inferring hidden variables, etc. And so things like MCMC, EP, variational methods, and even other new inference algorithms can be used on the same model, okay? So you really need to have a toolbox of components for your models that you understand and are comfortable with, like a Gaussian distribution or Poisson distribution or, you know, an infinite mixture, whatever the components in your toolbox of components. You put them together in a way that makes sense for your application. And then you say, how do I do inference in this? And then you go to your separate toolbox of inference methods. And if one of them doesn't work, you try a different one. And I think it's sort of important to make this distinction just because sometimes analyzing something is much more complicated if you mesh together the model and the algorithm. Okay. So now I'll just get to some points for discussion. So the first few points are just kind of, you know, my personal views on some myths and misconceptions about Bayesian methods. And I don't want to rant about this too long, but I think it's useful to kind of have them on a slide to be able to talk about them. So one of them is that, you know, I sometimes hear people who are maybe perhaps a bit naive about modeling say something like, oh, I'm not comfortable with Bayesian methods because you're making all these assumptions. I want methods that don't make assumptions. And I hear this surprisingly often. I mean, the answer to that is all methods make assumptions. In order to do anything that involves predicting, you have to make some sort of assumptions. Okay? If you don't make assumptions, the only thing you can do is you get your data set and you spit it back. You know, the identity map, you know, the same data, you say, oh, I'll tell you what my model is. I saw this data. That's my model. That's the only thing that doesn't make any assumptions. Okay? So without assumptions, it's impossible to predict. What the Bayesian framework does is it forces a sort of, you know, almost obsessive transparency in your assumptions. You have to write down all of your assumptions in the language of probability theory. And what that means is that then people look at it and your assumptions are so obvious they start questioning them. I actually think that's a good thing, right? If everybody had to be forced to write down their assumptions in a common language, then we could all question each other's assumptions. And you know, you would get different answers given the same data. That's because people make different assumptions. Okay. So whenever I see a method I don't understand, I try to figure out what are the assumptions that went into that method. What behavior will this method have, and so on. Okay, here is a second misconception, which is something like, if, you know, it comes in the following form. I don't really like Bayesian methods because I worry I don't have the right prior. And if I don't have the right prior, you know, I won't do very well. And it's certainly true. You can really badly abuse Bayesian methods by putting in ridiculous priors. But there's no such thing as the right prior from a subjective Bayesian point of view. Certainly a poor model of any kind, whether it's the prior part or the likelihood part, whatever aspect of your model, if it's a bad model, then it's going to make lousy predictions. So the point is, how do we guard against that? Well, the model all components of it, the prior and the likelihood, should capture a reasonable range of possibilities. And you can only do that perhaps by some introspection, some intuition about what these distributions are, and then some maybe sampling from your prior. When in doubt, you can choose vague priors. Basically, it shouldn't stop you just because you don't know something. It shouldn't stop you from saying, well, what's a reasonable range? I'm sure you can come up to a point where you say, oh no, that's unreasonable, right? I don't want, a range from minus 10 million to plus 10 million. That's just silly. So at some point, you will be able to specify a range. Here is another misconception. A lot of people associate Bayesian methods with maximum a posteriori. So MAP is similar to regularization, but it really offers no particular Bayesian advantages. In fact, I would rather do regularization than MAP, okay? Because regularization, at least, I can analyze within a nice framework for thinking about regularization. MAP has the kind of unfortunate aspect that you might actually think that I'm trying to do something Bayesian. And in fact, one of the troubling things about maximum a posteriori is the following. Maximum likelihood is invariant to reparametrization. Okay, if I take my maximum likelihood fit for a Gaussian, and I say, instead of parameterizing it as mean and variance, I'm going to parameterize it as mean and log of standard deviation. The maximum likelihood fit is still exactly the same. It's invariant to that reparametrization. MAP is not invariant to reparametrization. So whether I called it a variance or a standard deviation or a log variance actually matters when I do MAP. That just seems terrible, all right? That's totally irrelevant information. It shouldn't matter. In fact, give me any simple problem and any value of the parameter, and I can reparameterize the problem so that the map lies at that point, okay? The way you do that, by the way, if you're trying to think about it, is you reparameterize in a nonlinear way, so you squeeze the parameterization around that point, so your density, your prior will have to go up, and your posterior will go up around that point, and you stretch it out everywhere else. And then my map now will be at that point. So that just seems perverse, and for that reason, we should be careful about map. And importantly, from a more practical perspective, it doesn't offer the advantage of averaging over your uncertainty. People don't seem to like Bayesian methods because most Bayesian papers don't have a lot of theorems and proofs at the end of them. They're full of I ran this MCMC and then I did this and then here's a plot of something or other. It just doesn't feel as hardcore mathy or whatever. Well, one of the reasons for that is that a lot of the general theoretical properties of Bayesian methods are sort of known, and it's not really necessary to rederive them every time for every new Bayesian method because you can appeal to some of the general results. But more interestingly, rather than applying Bayesian theory to analyzing Bayesian methods, I think it's very interesting to think about applying frequentist-style generalization bounds in frequentist theory to understanding Bayesian methods. Things like PAC-Bayes, which was mentioned earlier today. And it's often possible to prove things like convergence, consistency, and frequentist rates for Bayesian methods. So think of the Bayesian method as a tool, and now you can analyze its properties independent of your prior assumptions that you made, just under some, for example, IID assumptions and things like that. Okay, I already talked about this point, that Bayesian methods are not necessarily generative. And then this last point, I think, is, anytime there's a myth, there is a truth behind the myth, okay? So, we have to be honest here. Bayesian methods don't have theoretical guarantees. Well, it's more like most Bayesian papers don't have a lot of theorems in them or anything, because they sort of appeal to general theorems that are there implicitly. It's also true that you often see Bayesian methods that are run on very small problems rather than on very large problems. And that's partly because doing integration is generally more expensive than doing optimization. Okay? Doing averaging or integration over a large parameter space is a more expensive thing than doing optimization. Okay? To do integration, you're supposed to try to visit the whole parameter space. To do optimization, you just have to find one point quickly. Okay? Now, recently, a lot of us have been trying to work hard at this and try to come up with inference methods, types of variational methods or MCMC that make it possible to scale to very large data sets. This is obviously an interesting area of research. And there are excellent results on largish data sets, and I'll mention some at the end. Any questions about this? Okay. So let's talk a little bit about the interface between Bayesian and frequentist methods. So just to contrast, the frequentist theory tends to focus on sampling properties of estimators. In other words, what would have happened had we observed other data sets from the model, or on things like minimax performance of methods. What's the worst case performance in an adversarial setting? And also frequentist methods tend to be based around optimization of some penalized cost function, although that's not necessarily the case. For example, if you look at a method I very much like for example, bagging, bootstrap aggregation, that involves averaging over parameters in a certain sense. Okay, Bayesian methods tend to focus on expected loss under the posterior, and they don't generally make use of optimization except at the point where you have to make a decision that minimizes your expected loss. Okay? Now, there are some reasons why frequentist procedures are actually very useful for Bayesians. One of them is, as a form of communication. Okay, if you have different Bayesians, if you have a Bayesian A that's done some analysis of some data, or some Bayesian model that's done some automatic analysis of some data, and you want to communicate that to other Bayesians or even non-Bayesians, then you need to see whether your conclusions are robust to your prior. Like, what would have happened with the same data but under different priors? And for this reason, it's sometimes useful to find priors that have good frequentist sampling or worst case properties. Moreover, priors with good frequentist properties sometimes can be very robust to misspecification. In other words, they'll spread their probability mass more than other sort of more informative priors, and in that way be robust to observing data that you really, really were not expecting at all. Okay. Questions about that? Okay, so just to recap, some pros and cons of Bayesian methods. So limitations and criticisms. Yes, they are subjective. It's often hard to come up with a prior, and the assumptions are usually wrong in some way, so one has to be careful. There's this question of the closed world assumption, that you need to consider all possible hypotheses for the data before observing the data, especially if you're trying to do something like model comparison. What is the space of possible models that you're willing to consider? They can be computationally demanding, and if you're going to use approximate inference, then it weakens those coherence arguments. Like, the whole point was we're going to be coherent about our procedure, but then we need to use variational Bayes instead of computing exact integrals. So in what way does that actually hurt your coherence? That's sort of an interesting question to ask. On the other hand, the advantages are it's it's a very coherent framework. in the sense that you write down your assumptions, you get the data, and everything you've done is what follows from the rules of probability given those assumptions and that data. So it's conceptually straightforward. It's very modular, and this is actually, from a practical point of view, quite interesting. For example, if I have a speech recognizer and I interface it with a language model, and I also have an acoustic model, now my language model is a probabilistic module, a component that predicts the probability of the next word given the previous words. I can modularly learn that language model in a better and better way, make better and better assumptions, plug that into my speech recognizer, and it should generally improve the performance of my speech recognizer. Similarly, I can take my acoustic model and tweak it for different acoustic scenarios, plug it in, and the whole thing becomes still a coherent inference engine trying to figure out what somebody is speaking under different environments, etc. And that same language model that I used in my speech recognizer, I can immediately plug it in to a compression algorithm and use that to compress text source, for example. The better my language model, the better my speech recognizer, the better my text compressor in general. Okay. So in that sense, it's nice and modular. I can plug these bits together, and their interface language is probabilities. Okay? And then finally, often the performance is good. Of course, this is the big empirical question. As an engineer, this is what we should generally just care about. Okay. So we need to show that in more examples. Okay. So this was just finishing off that first lecture. Wait, no, go away. Okay. So what I'd like to do in the next, hour and 15 minutes is to give you a very quick overview of graphical model background, parameter learning, and structure learning. Inference, parameter learning, and structure learning. So for this, it's useful for me to ask you, how many of you have studied graphical models outside of this summer school in the past? Okay. Almost everybody. How many of you have not studied graphical models? A few people. Okay, that's good. How many of you know message passing in graphical models? It's a slightly more advanced topic. Okay, and how many of you don't know it? Good. All right, so I think this will be useful based on that polling result. Okay, so graphical models are a way of representing knowledge about complex domains. And the basic idea is that if you have a complex domain in terms of some probabilistic model, then a graphical model is a way of representing dependencies between the variables in your model. The nodes in a graphical model correspond to random variables, A, B, C, D, E in this case, and the edges represent statistical dependencies between your variables. Well, why do we need graphical models? Why are graphical models so prominent in the machine learning community these days? Well, first of all, they're very intuitive. Graphs are an intuitive way of representing and visualizing the relationship between a bunch of variables. And of course, a lot of other fields use diagrams or graphs to represent relationships between things. From a statistical point of view, graphs are useful in abstracting out the conditional independence relationships between variables from the details of their parametric form. So if I have a graph like the one on this slide here, then I can ask the question, is A dependent on B given that we know the value of C just by looking at the graph. I don't have to write down all the equations or do anything like make an assumption about whether this is Gaussian or Poisson or Dirichlet or anything like that. I can make a general statement about what depends on what. And that is hugely useful from an abstraction point of view. And that aspect of graphical models becomes computationally very useful. So graphical models, because of this conditional independence, allow us to define message passing algorithms that implement probabilistic inference efficiently. So for example, we can answer queries like, what is the probability of the variable A given that we know the variable C takes on some value, by passing messages on this graph without having to enumerate all the variables and integrate everything out. Okay? So graphical models are really a very nice marriage of statistics, graph theory, and computer science. And this last aspect of it, the message passing algorithm aspect of it, is what's really made a difference in terms of scaling up probabilistic modeling to very large systems. So I'm going to focus on, I'm going to talk about directed graphs first, and then a little bit about factor graphs and undirected graphs. Now, directed graphs, sometimes called Bayesian networks, but they don't necessarily, there's a footnote here in that, for example, Bayesian networks, they don't have to be learned using Bayesian methods. It's just, you know, a naming convention that I don't particularly like. They're sometimes also called belief networks. But let's call them directed acyclic graphical models. It's maybe less contentious. These directed graphs correspond to a particular factorization of the joint probability distribution over the variables. So for example, this graph here corresponds to the factorization of this joint distribution into the probability of A times the probability of B times C given A and B, etc. Where in general what we have is that the joint distribution is a product of the probabilities of each variable given its parents in the graph. So the parents of C are A and B, that's why this term appears here, and that's the general form of the factorization for a graphical model, for a directed graphical model. Okay? And this factorization actually captures the conditional independence relationships between the variables. Okay. And so what do we mean by that? Well, given a graph, we can now say exactly what that graph says about the probability distributions that are consistent with that graph. What it says for any particular graph is statements of the form x is conditionally independent from y given v. X and y are some nodes in the graph, and v is some set of nodes. And that occurs when the set of nodes v separates x from y in the graph. So D separation stands for dependency separation in a directed graph. And I won't go over the definition of it just because it's a little tedious, but you could look through it and try to understand it. The idea behind this D separation is that we're trying to capture kind of intuitively whether all information from x to y and vice versa has to pass through the nodes V. If everything between x and y has to pass through V, then once we know V, x and y become independent of each other. Okay? I mean, you could think of a lot of analogies like, you know, the flow of information or the flow of electricity or whatever, you know, just think of it that way. And then the actual semantics are a little annoying, but, you know, that you can prove that these are things that follow from, what do they follow from? Guess. The sum rule and the product rule. Yes. They follow from the sum rule and product rule. If they didn't, and they follow from, that's the only thing they follow from. The sum rule, the product rule, and this statement. Okay? So it could take, 10 pages of Udea Pearl's classic book to prove this stuff, but all he's doing is showing you the sum rule and the product rule and the factorization. Okay? Now the corollary for this is that for any variable x, we can define something called the Markov boundary, and that insulates x from all the other variables. And that's the set of parents of x, children of x, and the parents of the other parents of the children of x. Given that set of variables, x is independent of everything else. Okay. So graphical models are kind of used in two very different ways. And I just want to give you a flavor for the two ways. One of them is when we write down a graph like this and we think of the particular variables as being something interpretable, like the temperature at this temperature sensor and the pressure at this valve, etc. And this is a graphical model that relates these things to each other. Okay? This is like as a way of doing knowledge representation in a particular domain. Another place where graphical models appear, is just in descriptions of statistical models like this. So for example, consider the following simple model. I have a set of n data points, generated IID from a Gaussian with mean mu and standard deviation sigma. Now, if I want to build a model of this, what that corresponds to is the idea that the joint distribution of x1 through xn, mu and sigma, factors in a particular way. This is the IID assumption. I said each of these depends on mu and sigma, right? And then I might have a prior, I haven't said that in the sentence here, but maybe my prior on mu and sigma factors in this way. Let's say. That's a particular model. It corresponds to a factorization of this joint distribution. We can rewrite that as a graph. And that graph looks like this. Mu and sigma are the parents of x1 through xn. And now, because often in graphs like this, we have repetitions of variables. So, we have these x1 through xn with this dot, dot, dot notation. A more concise notation is this thing called a plate, which just puts, in this case, a dashed box around x with a label here that indicates the number of times this variable is repeated in the graph. So xn is repeated big N times. Okay? This is just shorthand for this graph. So you'll see this sort of notation in a lot of machine learning papers. Okay. All right. So now let's talk about inference in graphical models. Consider the following graph. What is inference? Inference corresponds to evaluating the probability distribution over some set of variables given the values of another set of variables. For example, what is the probability of A given that we know the value of C? All right? So for example, assume that each variable is binary. How do we compute this? Well, here's a naive method. I write down the joint of A and C is the sum over B, D, and E of the joint of A, B, C, D, and E. There's 16 terms in this sum. Given the graph and maybe the probability distributions on each of the edges in the graph, I can actually evaluate this for all 16 of these terms. And then I can sum over A to evaluate these two terms. And then I can divide these by these, which give me these two terms, which gives me this probability distribution. Probability of A given C. Okay? This is a naive procedure because I went through writing down the whole joint distribution and evaluating all the configurations. And it took me 20 terms to compute this. Clearly, if I had 100 binary variables, this would be a really bad idea, right? Why? Right, because 100 binary variables have 2 to 100 possible states that you'd have to sum over. But we know something about this joint distribution. We know that it factors in a particular way. So let's rearrange the computations while keeping them exact. So I take this same graph, and now, this is just anecdotal, for this particular factorization, I plug it in here. This sum is still expensive to compute. But I plug it in here, and then I notice something about this. I notice that E only appears here. So I can bring this sum over E all the way in here. And I can sum over E exactly because I know that the sum over E is 1 when I have the conditional distribution of E, or the two values of E. So this thing sums to 1. Similarly, I can take the sum over D and bring it in, and this thing sums to 1, exactly. So in fact, this whole thing simplifies to the sum over B of P of A times P of B times P of C given A and B. And that ends up being about 8 terms, depending on how you compute it. That first operation is 4 terms. The other 2 operations are 2 terms each. So what does that correspond to in the graph? That corresponds to the fact that I wanted to know A given C. Okay? It turns out if I know A given its parents, it doesn't have parents, is children, and the parents of its children, that would be B, then everything else is independent, right? So in fact, if I look at the Markov blanket of A, the only thing that depends on is B and C. So that's all I needed to have in this. I needed to have A, B, and C in these expressions. The whole rest of the graph, even if it has 98 other variables in it, just drops out. Okay? But of course, we don't want to do these things by hand for every graph. What we really want is general purpose algorithms where you write down the graph in some way on the computer, and the computer automatically figures out how to apply the sum and product rule efficiently with the conditional independence relationships that are encoded in your graph. And clearly, by doing this on sparse graphs, we can get exponential gains over the naive method. Okay. So how do we actually do this? Let's focus on a particular example of factor graph propagation. This is sort of an implementation of belief propagation that's particularly nice and simple to write down. The idea of this is you take your joint distribution, which is, in this particular example, let's say it looks like this. And you, instead of writing it as a directed graph, we're going to write it as a factor graph. This is just another graphical formalism, which with similar properties. I can talk about the differences if somebody's interested later. The way we write this is we write it in terms of a product of factors. So for each one of these terms in here, we write down a factor, which is a function of the variables involved in these terms. The first term is just a function of x1. The second term is a function of x2 and x1. So we can actually group those together into this factor f1, which is a function of x1 and x2. And we write the factor graph like this. The nodes represent the variables, and these filled dots represent the factors. So f1 is a factor relating x1 and x2. Similarly for f2 and f3 here. And we're going to focus on what are called singly connected factor graphs. The singly connected factor graph corresponds to one in which the underlying structure of the graph is a tree. Okay? In other words, there is, between any pair of nodes, there is at most one path. Okay? So this is an example of a multiply connected factor graph, or not singly connected factor graph. And I can tell you later, if you're interested, how to do inference in these graphs. Okay. Any questions about this? Okay, so that's just now the general description of what a factor graph is. The joint probability is written as a product of factors. So the joint probability here is 1 over some normalizing constant of the product over these j factors, where each factor depends on some subset of the vector of all the variables. And we have these two kinds of nodes, the variable nodes and the factor nodes, which I described in the previous slide. These factors are non-negative functions of their arguments. Okay? If the arguments are discrete, for example, if they're binary, then we can think of the factors as tables, with non-negative entries in them. Okay? So that's a factor graph. And now we're going to think about how to implement inference in a factor graph, how to implement a sum and product rule if you have a factor graph for your data, for your model. Okay, so here's some notation. Let n of x denote the set of factor nodes that are connected to variable x. So, for example, variable 4 is connected to factors 3 and 4. So n of 4 is 3, 4 in this case. And similarly, let's say n of f denotes the set of variable nodes that are connected to factor f. So it's a bit of overload of this neighborhood notation. Okay? So we can compute the probabilities by propagating messages from variable nodes to factor nodes and vice versa. And it's basically these two equations. Okay? We have, in general, messages from variables to factors. So here is the message mu from variable x to factor f. A message is going to be an unnormalized probability distribution. So if x is, it could be normalized if you want to. You can just keep track of the normalization constants. But a message here in this case is a function of x. So if x is binary, that message is a 2-by-1 vector. Okay? And the message from variable x to factor f is the product over all the factors h that are connected to x, not including the factor f, of the messages from factor h to variable x. So if we want to visualize this on the graph, we had a message from x to f. So let's look at this graph here. Let's say the message from x2 to f3 is the product of the messages from f1 to x2 and the message from f2 to x2. Okay? We take an element-wise product of these vectors coming in, and we rescale or not if we want to, and we pass them on in the other direction. Super easy to implement. Okay? The message from factor f to variable x is given by the following equation. The message from f to x is also a function of the variable x. It's the sum over all variables, not including x, of the factor f multiplied by the messages from all the other variables to that factor f. Okay? So again, it's taking incoming messages, multiplying them by its local factor, then summing out all variables other than the variable x that it's sending the message to. And I try to explain the notation here. So, the message from factor f1 to x2 takes the message from x1 to f multiplies it by the factor f1, which is a function of x1 and x2. It sums out x1, and that becomes a function of x2 that it sends on to x2. Okay? That's it. These two equations, if you run them in a particular order until no other messages are left to be computed, if your factor graph is singly connected, what you get, this is just a repeat of these two equations. This is a statement of the order. If a variable has only one factor as a neighbor, it can initiate this message propagation. Then once a variable has received all the messages from its neighboring factors, then we can compute the marginal probability of that variable by taking the product of all those messages and renormalizing it. Okay? Any questions about that? How many people have seen this before? Raise your hand if you've seen it before. Okay, quite a lot of you. How many people have not seen this before? All right. So, so this is very nice. This is a very general algorithm. It turns out that it's a generalization of things that have been very well known for decades. For example, if I take a hidden Markov model, the directed graph for an HMM looks like this. These are observed sequence of data, and this is a sequence of hidden variables that are meant to explain the observed data. In a hidden Markov model, there's something called the forward-backward algorithm. That's just factor graph propagation. And it shouldn't be surprising. It's not like, wow, what a coincidence. These two things that were invented by completely different fields happen to be the same algorithm. It's not surprising at all, right? Because they're following the rules of probability using a graph. They better be the same. If they're not the same, one of them is wrong, all right? Now, Kalman smoothing in a state space model, that thing that I took 2 semesters of, you know, could have been explained as just factor graph propagation with Gaussian variables as well. Okay. Now, there's a lot of nice software for graphical models. I've just listed a few of them here with some comments about them. There's a great resource that may be a few years old that Kevin Murphy generated, which lists a whole bunch of graphical model software toolkits. And you know, of course, different software toolkits emphasize different kinds of models and things like that. Okay. So here's just a summary of the basics of graphical models. Inference is the problem of figuring out the probability of the variables of interest given the observed variables, while summing out all the variables you're not interested in. That's the basic thing we're trying to do. For singly connected graphs, we have these things called belief propagation and factor graph propagation. Kalman filtering and forward-backward are special cases of that. Now, what do we do for multiply connected graphs? Okay. Well, if we want to do exact inference in multiply connected graphs, there is a very nice algorithm called the junction tree algorithm. It's been known since 1988 or so. And basically, you can think of this as converting your multiply connected graph into a singly connected graph, but over supernodes that correspond to combinations of sets of variables. You do that conversion, and then you run factor graph propagation on that converted graph. That's basically intuitively what it corresponds to. That conversion is not trivial. There might be many ways of converting it, but you know, that's the basic idea. That can be very slow because that conversion of your multiply connected graph into a singly connected graph over supernodes is something that could be kind of expensive. It could end up with supernodes with exponentially many states in them. So in practice, what's actually done most often is to just run factor graph propagation, acting like the graph is singly connected when it's not. So close your eyes and press the go button, and cross your fingers and hope for the best. Okay? There's a lot of analysis of that, and I could say more about that, actually. That's called loopy belief propagation. Okay. Yes?
I was wondering if you can provide a sketch, proof sketch for the loopy belief propagation.
Proof sketch for loopy belief propagation. Okay, so I can certainly give you a sketch of a sketch. Hyper sketch. So, in general, loopy belief propagation, which is just factor graph propagation or belief propagation on a graph that has loops, like we saw before. Sorry, I don't know what happened here. Okay. In general, this is a loopy graph, a very small, easy loopy graph. But in general, that algorithm is not guaranteed to converge. Okay, so you could run these messages and the beliefs would keep going up and down, up and down. It's possible for that to happen. If it converges, it might not give the right answer. In some special cases, it's been analyzed and shown to be able to converge. For example, in the Gaussian case, it's been analyzed by people like Yair Weiss. In graphs that have a single loop or a few very large loops where the influence becomes weaker and weaker, then you can show convergence of certain kinds. And there is a very nice theory that's been developed around this based on an idea called the beta free energy, where essentially what people have shown is that loopy belief propagation in a graph, if it converges to fixed points of the beta free energy. Okay? And, okay, I think that's what happened. Right. The other thing that's interesting about loopy belief propagation is that this beta free energy interpretation means that we can now come up with convergent approximate inference algorithms for these kinds of graphs that are based around minimizing that energy directly rather than applying loopy belief propagation. And then the last interesting thing I want to say is that factor graph propagation or loopy belief propagation in multiply connected graphs is also equivalent to a particular form of the expectation propagation or EP algorithm. Okay. So there are very beautiful links between all of these different methods that are worth knowing about. Okay. So so that's the summary of inference. And then now for the next 45 minutes or so, should we take a 5-minute break? Okay. For the next 5 minutes, we're going to take a break. And for the following 40 minutes, just so that you're encouraged to come back, we're going to talk about parameter and structure learning in graphs.